I really appreciate David and Changhao coming out to share what they know with us. Please give them a round of applause.
So thanks for the introduction, Stephen, and thanks for the organization of the whole conference. And my name is David Wei, and this is Changhao Jiang. We both work at Facebook on front-end performance. And we basically start to work on the front-end performance from last year. And after 1 year, we have some experience to share with all of us here to see if we can make the whole Facebook and all the other websites faster. So I will first spend like a few minutes to talk about why we think site speed is important. I'm sure that everyone here agree, but I will just show you a little bit of the advertisement of why we focus on site speed. And then we will talk about 4 different projects that we use in Facebook to make the site faster. And then we will summarize the results. So first, site speed really matters. Why? We have more than 200 million users in Facebook, and every day they have more than 4 billion of page views. And I always talk to the developer about the following. Think about the scale we have. If you speed up the site by 10 milliseconds per page, that means 1 man-year per day you save for all the users. And if you slow down each page by 10 milliseconds, over the whole year, accumulatively, over all the users, you are killing 5 human life of time among all the users. So that's why we really matters. We really think that site speed really matters, and we focus on that a lot. And on the bottom line side, we also have a lot of experiment to show that if you increase the site speed, the click rate will actually be increased a lot. We had one experiment to show that we speed up the site by 600 milliseconds, and the click rate is actually increased by more than 5%. And we are working on a more detailed experiment and A/B testing, and we hope that we can share the data very soon. And on the other hand, for Facebook, site speed actually is a big challenge. There's at least 4 challenges that I think is unique for Facebook that is very difficult to make the site faster. The first one is the agile development environment in Facebook. So the code in Facebook changes a lot. Every week we have a new release, which will push a new version of Facebook, and with like hundreds of changes. And every day we have tens of changes. There's no point of the time to say that the code is stable. It's never stable. And you never can say, let's stop the development and focus on optimization. You have to live with this agile development environment. And the second is the deep integration. It's not like Google or Yahoo that each page is a functionality. In Facebook, each page has tens of functions. So the right side is my Facebook applications. We have more than 10 for my site. And this all function will appear in the home page and the profile page and a lot of other pages. So it's very difficult to identify if there's a regression, which function introduced the regression. Third, there's a viral adoption. So when you push a product, you don't even know tomorrow there will be 1 million of users use your product, or there may be hundreds of millions of users use your product. You basically don't know. It depends on the users. And one of the products we have is that we push it for almost a year. No one was using it. But suddenly there's one day that suddenly everyone feels that it's happy and they use it a lot, and at that day it crashed our servers. And finally, there's a heavy interactive website. So we have on-screen chat bar, we have type ahead on search, and all this is really cool for the users. But on the other hand, it also brings in a lot of JavaScript, and JavaScript is very slow. So in summary, if you look at Facebook, this is a special site that has unique challenges to make the site faster. And if you look at these challenges, they are actually making Facebook as a very good and paradise place for people who want to build new things. Basically, you can say that a person can build something tonight and make it usable tomorrow, and a lot of users can use it. So we don't want to get rid of this culture. But on the other hand, we also want to make sure that the site can be run fast with these cultures. So the following, I will share our experience on how we deal with these cultures and still make the site faster. So before going to the detail, I want to define the problems. So when we talk about site speed, what it is. So from our definition, the site speed is the end-to-end latency experienced by a user. Basically, from the time that user clicks something to the time that the page is presented to the user at the browser, which is also interactable. So user can click something and can chat. So this process has three components from our understanding. The first component is the network transfer time, which is from the time that the browser sends a request to the Facebook server and return. This is controlled by the round trip. And the second component is the server generation time, which is the time spent on the server side to generate the HTML content. And the third component is the client render time, which is the time the browser gets the HTML, download the multimedia content like JavaScript, CSS images, and render the content and run the JavaScripts. Finally present the page to the user. So at Facebook, the breakdown is the following. 50% of time is spent on render time for all the users. And 25% are spent on the network time. And another 25% is spent on the generation time. So in this talk, we focus on the render time. So the following, we will talk about 4 different projects we have in Facebook to make the site faster. And the first one is the site speed monitoring, which we have a code name called Cavalry. So to make the site faster, the first question you would ask is that, what is the speed of the site at this time? So usually, to answer this question, there's 2 different approaches. One approach is that you sit in the office and run a Facebook page and see how fast is it. And you can use YSlow, Google Page Speed, and a lot of other tools to measure that. This is great that it gives you a lot of inside information. But on the other hand, there's a problem. If you use your own page as a sample, it's hard to guarantee that your page is typical for all the users. We learned a lot of lessons from this in the past. So for most of the Facebook employees, their page is actually more heavier than the typical user. And when we try to focus to optimize these employees' pages, we actually miss the majority of the user. And also, the employees' browser have a lot of add-ons like Firefox, IE development toolbars. This all will actually make the measurement skewed. So the other approach is that you sample all the user space. So that's what we are finally taking approach. So we sample 1 out of 10,000 page load by JavaScript and measure a few time points. The time point is shown in the red arrow. Basically, the server starts to send the data, and the first byte of HTML arriving on the client side, and the finish of JavaScript, and the content loaded, which is the onload event, and finally the time that we report the data. So there's one thing I want to say about these slides is that if you look at the detail of the Fireback graph, we are actually violating the rule of YSlow. We are actually pushing the JavaScript before the CSS, and there is a reason for this. So if the JavaScript is loaded sequentially, it is true that you want to put the CSS on the top, because then CSS can be loaded first in parallel and then JavaScript sequentially. But if you can make the JavaScript loaded in parallel, it's probably not the case. If you put the first JavaScript, which is blocking at the beginning, and all the JavaScript can actually be loaded in parallel unblocked, and then the CSS will be in the same parallelization section, unblocked, and the image. So basically, the only blocking point of this page is the first JavaScript. And after that, JavaScript, CSS, and image are all downloaded unblocked. That's why we actually choose to violate the rules. So once we get the sampling data from the users, we integrate it with the generation time and the network time measurement and put it into a log, a Cavalry log. And then we have a daily site speed monitoring. So that's great. Every day we can say, hey, the site is faster or the site is slower. So the second question comes in after you know what is the site speed. So when you see the site is slower, the first reaction is, who made that slower? Sorry, we don't know. Why we don't know? Because we have so much function in the same page. And if one of the functions is slow down the site, everything is slowed down. So the second thing we want to answer is, who made it slower? To answer this question, we hook up the sampling system with our launch system. So the launch system actually can give a bit of information for each sample to indicate what are the new functions that we are releasing to the user in this sample. So our launch system actually can do like 50% of launch, or 10% to 90% launch. So during the launch process, we can actually monitor what are the samples that is affected by a particular project. And once we get this sample information and the launch information, we can run a regression test and regression analysis and identify who made it slower. So this kind of answers the second question. It is still not answering the question like if someone launch a system, launch a project from 0 to 100% tonight, then there's no chance we have enough data to analyze it. But in many cases, we answer the question. So once you find out who made it slower, what is the third question someone will ask? So the team will say, oh, I am responsible for that. But why it is slower? And what makes it slower? So that's the third thing. So looking at the number, like 2 seconds, 3 seconds, you really don't know what happened. And what really comes in to help us is YSlow and Google PageSpeed and all these great tools. So we actually implement some kind of a YSlow-like metrics on all the users, all the samples users. And besides the time measurement, we also have these technical metrics, like how many number of DOM in each page, how many number of bytes in HTML, how many number of JavaScript in each page. And we combine this into the log, and then we can give an answer to the developer saying that why your page is slower and why your function is slower. So in summary, my understanding is that there's 3 W in the performance monitoring. You want to ask 3 questions: what, who, and why. So what we did is that we use user-based measurement to answer what is the size B, and we integrate our measurement with the feature launching tool to answer who made it slower or faster. And finally, we use a lot of technical metrics, thanks for the YSlow team and the Google Speed team, to define an actionable item to fix a regression. So that's the first project. And the second project we want to talk about is the static resource management, which we have a codename Haste. So what is static resource? Our understanding is static resources are all the resources that are not changed, like JavaScript, CSS, and icon images. So the first question is, why do we need to manage these resources? So I will give you an example, which is really a real example in Facebook. And it actually happened a lot. So from day one, some Spark engineer will say, hey, I have a great idea. Let's write a page. The page will have 3 functions, A and B and C. And let's stick with the YSlow rule, put all the CSS at the top. Then you will write the following. I will print a CSS tag for A, and then the tag for B, and then the tag for C. And then I print the HTML for A and B and C. That's great. And you can launch it tomorrow, and user can use it. From day 2, some engineer is smarter, and they run a YSlow again, and find out that, hey, A and B and C are always together. You should package them. So you can reduce the number of HTTP requests. That's also great. Awesome. Then the site is also fast. And day 3, feature evolves. Suddenly, we want to decide that we don't want to render the HTML for feature C unless a user signs up. OK, that's great. What happens is that now, for the user does not sign up for feature C, you are still sending the CSS rules for C in the package. How about day 4? It turns out that no user actually used feature C at all. Let's deprecate it. No one will remember to delete the C in the package. 1 month later. And then we run a YSlow again. We violate another rule, which is that you have too many CSS rules on all the pages, which is unused. And you probably have a lot of cases if you have such a fast-running site. So what is challenging here? 3 things. Deep integration. For each page, you have like 3 or 4 or 5 features. Second, viral adoption. You don't know which feature is used by which users. Third, agile development. You develop so fast that you don't have time to slow down and think about optimization. So what's our response for these challenges? As I said, we don't want to break the culture, and we want to keep this culture to let people move fast. So our response is that 3 rules. The first rule is that you want to separate the declaration of requirement and the delivery of the static resource, separate them. And for the requirement declaration, they should be always living with the actual HTML generation. And third, for the actual delivery of the static resource, we will have a global optimization for you. I will give you an example. Go back to day 1, when you want to start the project. Instead of printing out the CSS and at top by yourself, I actually ask you to just declare the requirement. Basically, you can say, I require static resource A, and require static resource B, and require static resource C. And this requirement declaration should be always in the same function as the render of the HTML features. So if you delete a feature, or if you don't render the feature, you will also do not run the required declaration. And at the end of the day, after you declare all the resources, we will deliver all the required resources for you by our infrastructure system. And we will run optimization for these resources. And finally, we will print all the HTML. So by separating the declaration and the actual delivery, we can do a lot of things. One thing that is very helpful is to do chase analysis of all the usage model. So on the online process, you can declare require A and B and C, and we actually log all the usage pattern for each page, so that you found that for page A and B and C, they are always used together, and you should actually always package together. And tomorrow, if C is not used, you can actually remove C from the package. And in the offline process, we run a clustering algorithm to optimize the package and create an optimal package for all the sites, all the pages. And when we deliver all the CSS, we will actually generate and send the optimal package for everyone. And the engineer will be transparent about that. They don't even need to worry about optimization of the package, and we will do it for you. So this is the result of the trace-based packaging. In November 2008, when we started packaging, our JavaScript code base is like 4.4 meg. We have 29 JavaScript packages in the home PHP. That's a lot. And half a year later, the code base increased. Like the number of JavaScript increased by 60%, and the bytes increased by 30%, while our package number is actually reduced by 14%, by half. And the actual bytes sent to the user is actually also dropped. The same story is in the CSS. And the number of CSS increased a lot, and the number of CSS bytes increased, but the number of package and the number of bytes actually reduced. It also can use for image spriting too. We have thousands of images for GIFs. So here's a quiz. For all these images, what kind of image we should package together or sprite together? There's no clue about that if you just look at these images. Here's the answer. It's actually pretty straightforward if you look at the answer. If you want to have a drink, and you want to drink a beer and you want to drink a champagne, and user usually have this GIF together, and you want to sprite them. And if it's your birthday, you usually receive a happy birthday cake and the candles, and then you want to package them together. So if you look at the images themselves, you have no idea. But if you look at the trace, it's pretty intelligent. So in summary, once we separate the declaration of the requirement and the actual delivery, and if we run trace analysis on the declaration, there's a lot of automatic optimization we can do. We can do intelligent package system. We can do intelligent image spriting. We can also do intelligent progress rendering. I will add one more sentence on the progress rendering. So if you look at all the trace, you actually know that what are the JavaScript and what are the CSS and what are the images that are always used for a certain page. And before you generate anything of this page, you can flush out all the JavaScript and CSS and the image tag for this page. And the browser can start downloading these static resources while the server is generating the HTML. So we have been doing the experiment on this, and the initial result is very promising. So these are the projects I've talked about on static resource and on measurement. And Now, Changhao will talk about more on the JavaScript magics.
All right. Thanks, David. Hello, everyone. I'm Changhao Jiang. So in the rest of this talk, I'm going to talk about 2 projects we developed at Facebook that proved to have significantly improved our front-end performance. So the first project I'm going to talk about is called QuickLink. QuickLink is an internal project, internal name for the project that tries to Ajaxify the whole website. Before I dive into the details why we want to Ajaxify the whole website, let me try to give you some motivation. So the reason is because we found that most user sessions on the Facebook website actually contains multiple page views. So for example, if you log on to Facebook website, you usually start from your home page. And then you read through some of your newsfeed stories, click to your friend's profile photo, profile pages, photo albums, or go to, and then you come back to your home page, and then you read through some other newsfeed stories. So this is very typical. And it turns out in the current browser model, the browser actually doesn't do anything special if the pages are from the same website, except caching the JavaScript, CSS, and images. These are good things, but they are not good enough. The reason is because at Facebook, we have developed a lot of products that are purely implemented in JavaScript, which relies heavily on JavaScript. So what QuickLink tries to do is to eliminate all this redundant work that browser has to repeatedly do for each of these page views in the session. So the idea is pretty simple. Instead of relying on the browser to transit from page to page, we can use Ajax to fetch the content for the next page, so that from the browser's point of view, the user is still staying in the original page. So the browser wouldn't unload the resources and reload the resources for the next page, even though most likely they are always the same. And from the end user's point of view, they can navigate around the site from page to page. That's exactly the same as if there's no Ajaxification. So next, I'm going to describe from the end user's point of view how QuickLink works. Suppose a user is on the Facebook website, and when he clicks on the link or click on the back and forward button, then QuickLink is going to intercept that event, and then send an Ajax call to the server to fetch the content for the next page. And when the receive comes back from the server, QuickLink is going to first blank the content area in the page, which is the area that excluding the top navigation bar and the Facebook chat bar. And after that, QuickLink starts to download CSS and JavaScript resources in the page, required by the page. And after that is done, QuickLink is going to dynamically swap in the HTML content for the next page. And then the transition is done. So that is the high-level view of how QuickLink works. Actually, there are quite a few building blocks that enables QuickLink. So in this talk, I'm going to cover some of them because I don't really have time to all of them. The first building block that I'm going to talk about is link controller. This is a JavaScript library that allows us to intercept users' click on the event on the link. So we QuickLink use that library to dynamically attach custom onClick handler to all of the links in the page in the unload event, in the unload handler of the very first page. And in the onClick handler, what QuickLink does is that instead of giving back the control to the browser, it sends an Ajax call to the server. And the response from the server is a JSON encoded data structure that includes information about the HTML content for the next page and the CSS and JavaScript resources for the next page. And so the browser is so quickly then dynamically download all these static resources. After that, it swapping the HTML content and then execute some JavaScript initialization code for the next page. So after we use a link controller to attach this on-click handler, then the user is able to transit from page to page via Ajax. But there's no way for a user to click back and forward button to go to the previous page or the next page. So that is what History Manager is used for. History Manager basically is a library that enables the back and forward button for Ajax requests. There are actually quite a few open source choices for this functionality, but most of them takes advantage of the property that if you change the hash property of the location object, the browser is going to insert a new entry in the browser history. And then when user click back button, the browser is able to restore the previous value for the hash property of the location object. So History Manager set up a timer function that periodically posts the value for the hash property of the location object to detect when the user clicks back and forward button. Quicklink uses this feature to detect when user click back and forward button and encode the page URL as the hash value of the location. So that's what I highlighted here. So this enables Quicklink to be able to go to the previous page when user click back button. And the third building block is the bootloader library that we used at Facebook. This is a JavaScript library that allows us to dynamically download resources via link tag injection or script tag injection. This is pretty commonly used in JavaScript, so I will not talk too much details about it. But in addition to that, bootloader also keeps track of what resources have been downloaded. So so there's no resource that is going to be downloaded twice. And there are some other details about Quicklink that I don't have time to cover, so I'll just briefly mention some of them. In the Quicklink world, all pages are going to share a single JavaScript global space. And as user navigate around in the site from page to page, all the CSS rules required by all of the pages are going to accumulate it over time. So it is important to ensure that all the resources required by one page is not going to interfere with the resources required by another page. And another thing is that we need to simulate some browser behavior when user Ajax from one page to another. For example, we need to simulate a spinning cursor and the status bar in the browser, something like that. And we also need to support permanent link, which allows a user to cut and copy paste the URL and send it to another friend via email or instant messenger, so that the other friend can just click the link and go to the page that the original user wants to show him. Right now, Quicklink has already become a key component in our front-end infrastructure. It's been turned on for more than almost a year now. Right now, it's turned on for Firefox and IE users, which account for more than 90% of the users on Facebook. And about 60% of the page hits to Facebook websites are all Quicklink requests that are Ajax calls issued by Quicklink. And this graph shows some performance improvement that we achieved from Quicklink. It compares the client-side render time for full page load and Quicklink. For profile page and home page, these are the two most popular pages on Facebook website. As we can see that the blue bar represent the client-side render time for full page load, which is the traditional page transition model offered by the browser. And Quicklink, the purple bar represent the client-side render time for Quicklink. And as we can see, there's a 40 to 50% reduction in client-side render time just because of quickling. So in the next, I'm going to talk about PageCache. PageCache is a client-side caching system that we developed to cache users' visitor page on the, in browser. So why we want to cache users' visitor page? The reason is pretty simple, because we found that in the user session, there are several pages that are likely to be revisited very soon after they are visited for the first time. One example is that we found homepage is accessed every 3 to 5 page views. And also because of back and forward button, the recently accessed page is likely to be re-accessed very soon. So if we can somehow cache user's visitor page at the client side, then when user goes back to that page, we can directly serve the page out of client-side cache instead of having to go back to the server and regenerate this whole page. So how PageCache is implemented? PageCache actually is implemented on top of quickling. Remember, this is the slide that I just showed you explaining how quickling works. PageCache essentially just adds 2 additional steps to this process. Specifically, in step 3, when quickling receives a response from the server, it first saves the response in the client-side cache. And later, when user go to another page, quickling first to check whether the target page is already in the cache. If it is, then quickling can just fetch the content from the cache instead of going to the server to fetch to regenerate it. This all seems pretty simple and pretty easy to understand, but actually there are quite a few subtle issues that we have to deal with in order to implement PageCache correctly. So first issue is that because Facebook is a very dynamic and fast-changing website, even in a short period of 1 minute, it's likely that the cached version is already obsolete because there might be some updates on the, some latest stories that happen to your friends. So this, for example, if you go to your homepage for the first time and the homepage gets cached, and then you go to another page, and 1 minute later you come back to your homepage, we want to make sure that you will be able to see the latest stories that just happened in the past 1 minute. And also, we want to make sure that the user will not see the same ads again and again. So how we solve this problem? It's pretty simple. We actually just use Ajax call to fetch incremental updates to the cached version before we show the cached page to the client. We send an Ajax call to the server to pull for incremental updates and then apply it to the cached version and then show it to the user. So this is used by homepage to refresh ads and fetch latest stories. And the second issue is in-page writes. So suppose that when you go, so this example gives you a scenario. For example, if you first go to your homepage and that page gets cached, and then you find an interesting news story, you made a comment on it. Because the page is cached before you made the write operation, then if later you come back to your homepage, if PageCache just directly restore the cached version, then you will not be able to see the comment you just made by yourself. So this is very weird user experience. So we want to make sure that user can see his own action performed on cached page. And the solution to this is that we automatically record all the write operation that the user performed on the cached page. And when user comes back to the cached page, we automatically replay those recorded operations to restore to the state when the user left the page. And the third issue probably is the most trickiest issue. It's a cross-page dependency problem. So to give you an example, on Facebook homepage, on your homepage on the top right corner, there's a request box that shows how many friends request event invitation that you have, and you can click through the link and go to your friend request page. You can accept or decline some of your friends' requests, and when you come back to your homepage, we need to make sure that the count information for your friend request is correct instead of just showing the cached version, which is already obsolete. So this problem is different from the previous one because the user actually made the right operation in a different page instead of the cached page. So how do we solve that problem? The solution is server-side invalidation. So the idea is that we instrument the server-side database access API, and whenever we detect a write operation to the server, which means that the user has changed some persistent state on the website, then we can send a signal to the client indicating that, hey, something has changed. Then the client can decide whether or not to invalidate the cache based on the signal it receives. So right now, PageCache is deployed on production. Right now, it's only cache pages in memory, and it's only turned on for homepage. And this graph shows that shows a week-over-week comparison of the page hits to homepage 1 week after we launched the PageCache. And it indicates that PageCache is saving 20% of the page hits to homepage, which is not only the most expensive page to generate, but also the most popular page on Facebook website. And this graph shows the performance improvement from users' perspective. So user perceived the client-side render time. Remember, we mentioned that QuickLink is saving about 40 to 50% of the client-side render time compared with full page load. And PageCache actually further improves QuickLink's performance by 3 to 4 times in client-side render time. Okay, so that's the end of the materials that we have prepared to talk about. And to conclude, in this talk we mentioned that first it is important to do performance monitoring in order to understand your performance, and we need to answer the questions about what has been slow or fast, and who made it that way and why. And also intelligent adaptive static resource management is very important, especially for fast changing websites. And also Ajaxify a website where pages in the user session share a lot of common redundant work can dramatically improve the performance. And caching users' visit page in the client side can not only improve user perceived performance, but also can significantly reduce your data center cost. So that's all the material we have prepared. Thanks. Yeah, so if you have any questions, we still have some time to answer. Yeah, please. How we measure client-side render time? Oh, okay. Let me let David answer this question.
Okay, so basically we use JavaScript. So whenever the first byte of the sampled page will be a JavaScript to record the first starting time of the render time, and then the onload event will be the time of the end of the render time. And there's also DOM content ready, like what you see in the Firebug, and you can introduce more like the end of the last JavaScript for downloading. And these are the available point of events that you can measure in the client side.
Does the method you use to measure change
Can you say it again?
Do your latency measures, the events that you're measuring change now that you're using a new infrastructure?
I probably can. So the question is that does the methodology of the measurement change with the new technology like quick link and PageCache? The answer is yes, but on the other hand, the whole quick link will simulate all the browser event like onload and dump content ready. So we can use the same conceptually event to measure, but physically they are changed, yes.
Do you have more business metrics or customer metrics about the impact of Changhao on your users?
We don't have a detailed understanding at this time, but we definitely is running the experiment. Actually, yesterday, the Microsoft and Google talk actually inspired a lot, and we are actually running the experiment now. And we do have some preliminary result before, but it's not complete, yeah.
So I guess the question is that we showed that quickling has improved client-side render time, but we haven't shown any performance regression or improvement on the server side.
Yeah, on the amount of request drops.
Oh, so that's a good question. So actually, quickling not only saves the client-side render time, but also saves the server-side generation time, because in quickling, for each of the new page, we don't need to regenerate the Facebook chat bar and the top navigation bar that are common to all of the pages. And so this actually has some savings on the server side.
You don't have any numbers?
We do have some numbers, but I don't remember it off the top of my head. The saving is not very significant compared with the actual content contained in the page. Yeah, so quickly, so the question is that when we send a quickly request to the server, how do we know which content are new? So the answer is that quickly is not only a JavaScript infrastructure, it also includes the server-side library, so that allows the developer to, so basically the PHP part of the quickly infrastructure will automatically only generate the content area that excluding the top navigation bar and Facebook chat bar. So from the developer's point of view, they don't need to know about Quicklink, they just write a new page. But Quicklink library will automatically only extract out the content in the middle. Does that answer your question? Oh, I guess you are talking about PageCache. So in case of when we restore a page from PageCache, PageCache can send an incremental, can send an Ajax call to the server to pull for incremental update. And in the Ajax call, we attach some information about the timestamp for the information for the latest story that are cached, and then the server know what is the latest story to send to the client. Okay, thank you.